Welcome in my channel Digital World. In this video, we will learn how to write VHDL code for 4-bit ALU. So click on ISC Design Suite 14.7. This is from Xilinx. So this is the software ISC Project Navigator. So here click on OK. Now click on File. Select New Project. This is our folder F drive VLSI. Just create one folder ALU _ test. Click on Next. These are device specifications. Family Spartan 3E, device XE3S250E, package CP132 and speed is 4. In synthesis tool, choose XST VHDL or Verilog. Simulator is ISim Simulator. Preferred language is VHDL. Then click on Next. Click on Finish. Now this is our project ALU _ test and this is our device XE3S250E. So click on this device. Then right click New Source. Then select VHDL model and give file name. So we are writing code for 4-bit ALU. So I'll give the name ALU _ 4-bit. Click on Next. Here we have to check entity name is by default. Architecture name is also by default. So you should give input. So there are two inputs A and B. There is one more input we are taking selection line because we are performing multiple operations using ALU. Few logical operations and few arithmetic operations. Then we are taking output, that is of out. Now I will explain you how to give inputs and outputs in code also. So click here on Next. Click on Finish. So there are multiple green lines. These are comments. So select it and delete it. Click on Zoom In. So this is Zoom In option. So just give heading. For comment we are using double dash. So we'll give the comment or title of our code VHDL code for 4-bit ALU design. So here first part is library declaration. By default library is std_logic 1164. Additionally we are adding two more libraries. We have to rename this as unsigned. So just remove this and you can put unsigned library. Add one more library that is used for arithmetic operations. So just remove this and add arith. So there are three libraries we can use in VHDL. This is comment. So we can remove this comment. So the first part in VHDL is to declare libraries. Second one is entity declaration ALU. This is 4-bit ALU. It consists of port. So IOs are declared over here. A and B direction is in and the type is std_logic. ACL direction is in std_logic and OP is my output. Type is same std_logic. Now if you want to design 4-bit ALU, I have to modify this A and B as a vector. So we can do this in the previous window also, but I want to explain you what is difference between std logic and vector. So std logic, it represents data only in single bit, either in the form of 0 or 1. But whenever we want to go for vector, so here we can define multiple bits. So as A and B both are 4-bit, I will define A as 3 down to 0. So this indicates that A is of 4-bit. Similarly, I want to go for SCL. So SCL is a select line. I want to perform multiple operations. So for example, we have to perform 8 operations. So we can edit this SEL that is of 3 bit. So in this way we have to define SEL that is of 3 bit and OP that is of 4 bit. Now we have to write architecture. So this is syntax of architecture. This is begin. Now we have to define process and write case sensitive signal. So there are 3 case sensitive signal. The first one is A, B and third one is SEL. After that we have to write begin for process. So the first begin is architecture begin and second begin is a process begin. Now we are using case statement. So write case SEL is. Right, SEL is our input. So we have to use when statement. So write here when, then 0 0 0. There are 3 bits we are using. So when SEL is equal to 0 0 0, then we have to perform operation, that is OP assigned to A plus B, and then we have to put semicolon. So this is our first operation. When selection line is equal to 0, we have to perform addition. So we have to copy this for multiple times and then we have to change our select line. So the second case we are taking when select line is 0 0 1, then we have to perform subtraction. When select line is 0 1 0, then we will perform A minus 1. When it is 3, that is 0 1 1, then we can perform B minus 1. The next one is 4, then we can perform A and B. Next one is 5 1 0 1, then we can perform OR operation. So modify code like this. Next one is 6 1 1 0, this is 6, then perform NAND operation. And the last one, this is 7 1 1 1, then we can write NOT operation or inverter. So this is NOT of A. So in this way we can go for some logical operation. So first 4 are arithmetic operation and the last 4 are logical operations. In addition to that, we can write other conditions with respect to case statements. So when others, then we are not performing anything, so we can write null. So in this way we can use case. So this is start of case. Now we have to end this case. So you can write here end case. Then this is start process. Then we can end this process. So just try to align it properly. So this is end process. And finally this is start of architecture. So this will be end of architecture. Now this is our VHDL file. Select it and save this file. Now click here on synthesis. Click check syntax, verify errors and warnings. So no error in your design. For example, we are removing this semicolon. Click here. Again you can see there is one error is here, syntax error near this operator. So you can click on this. So line number 24 you can check, and where semicolon is missing we can put it. Again save this, click on check syntax, verify errors, then click on synthesis. After synthesis, click on RTL schematic, select start with Explore Wizard, click on OK, then click on add and click on create schematic. So this is our ALU 4-bit. It consists of A 4-bit, B is 4-bit, SEL 3-bit, and this is OP, this is 4-bit. So you can click on this box and click here on zoom out, zoom to full window, and then you can see internal architecture of 4-bit ALU. So you can click on individual block and see the internal architecture generated by Xilinx tool. So this is called as RTL. Now click again on VHDL file. Now we have to synthesize this. We have to click on synthesis XST. Now we have to simulate this program. So you can select our VHDL file, right click, new source, select VHDL Test Bench, give file name, we can give name test ALU, click on next, click on finish. So this is our test bench file. You can click here on zoom and zoom it properly, remove comments, just write it, heading we are putting here test bench code for 4-bit ALU. Few things are automatically generated. So first one is library declaration. This is automatically generated. Comments we will remove. This is entity, then architecture. Between architecture and begin, first we have to define components. Components are same as our VHDL file. Then same IOs we can define as the inputs. So signal inputs are defined for A, B and C. All inputs are defined as a signal. The next one is we have to define outputs as a signal. So signal OP is output. Then here one constant. This is clock. We are not using this clock because this is sequential statement. Sorry, this is combinational statement. Clock is not required. Then in begin, this is our port mapping. Then this is clock. Select all clock parameters, right click, comment. We are not using, else you can remove this from our code. Clock is not required. Then this is stimulus where you can write your test cases. So the first one is we have 3 inputs A, B and SEL. So first what we can do, we can assign A is equal to 4-bit data. So we are assigning 8, that is of 1000. The next one is B. We are assigning next data, that is of 0001. This is B, put the semicolon. So we are keeping A and B remains constant and we are changing only selection line. So here SEL we are assigning. There are multiple cases we are checking. Right, so the first one is SEL is equal to 000. Then we have to use some delay, so wait for 10 nanoseconds. This is clock, we are not using this clock. So this is our first test case where A is 8 and B is equal to 1. So when SEL is equal to 000, it will perform addition of A plus B. So A is A and B is equal to 0001. So addition, that is OP is equal to 1001, means it's 9. Now what we should do, we will keep value of A and B remain same and we will change only parameters of selection line. Now the second one is, this is SEL. We are keeping SEL is equal to 001. So here we will perform subtraction, that is A minus B. So A is 8 and B is equal to 1. So after this condition we are getting A minus B, that is 8 minus 1. It will be 7. Now the same thing we have to repeat 8 times. just change values of SCL. So this SCL is equal to 0, 1, 0, 2. The next one is SCL is 3. Next one is SCL is 4. So right here, it is not necessary to maintain the sequence. We can give any condition at any time. It will work in the case statement. So this is 4. This is 2, 3, 4. Here we can give. This is 5. Next one is 6. And the last one is 7. So all 8 conditions are given over here. It is not necessary to give all. You can check any 2 or 3 conditions. But here for ALU, we will check all arithmetic and logical operations. So we will remove this weight. So it will go back to our initial condition because the condition is wait for 10 nanoseconds. If wait is there, then the loop will exit over here. So this is end process and this is end architecture. Now click here on simulation because in this simulation our file is available. So test_ALU, this is our file. Now save this file. So when this simulation file is visible, here is ISim Simulator is visible, and whenever we have to click on implementation, synthesis processes are available. So now for simulation, click on simulation dot. This is our file. Click here on behavioral check syntax. So check syntax first. No error in your design. For example, we are removing this semicolon. Save again. Click here on behavioral simulation. So there is error. So you click on error. So here the error is available. Click on here. Same error. So you can see there is error, syntax error. So we can go to that line and put the semicolon. Now again check behavioral syntax. Then click on simulate behavioral model. Yes, it is finished. Now this is our simulation window. So the first click on zoom to full view. So this is third option. So click here on zoom to full view and just zoom it, then drag it. Here you can see value of A remains same. You can see this cursor. A is equal to 100. So A remains same, and this is B. B is equal to 0001. So B remains same. Now we have to see output. So from 0 to 10 nanosecond, our selection line is 000. So when selection line is 0, then we have to perform addition of A and B. So A is 8, B is 1, so addition is 9. Next one is from 10 to 20 nanosecond, we have to perform subtraction. So A is 8 and B is equal to 1. So 8 minus 1, your output should be 7. Next one is from 20 to 30 nanosecond, we have to perform A minus 1. So A is 8, 8 minus 1 is 7. So this is 7. When it is 3, 0, 1, 1, then we have to perform B minus 1. So B is equal to 0001. So 1 minus 1, output should be 0. Next one is we have to perform AND operation when the selection line is 100. So AND operation of A and B, we can see here it is 0 because 1 AND with 0, 0, and here 0 AND with 1, 0. For 101, we have to perform OR operation. So OR operation is 1001. For 111, we have to perform NAND operation. So NAND of both. Next one is last operation 111. This is NOT of A. So A is 1000. So NOT of A is 0111. So in this way we can observe simulation. And after 111 in our test case we had given 0, wait for 10 nanoseconds, so again the loop will continue. In this way we can see the simulation of 4-bit ALU. Now close this window, click yes and click on implementation. Now the second part is we have to generate bit file and we have to upload this code on FPGA. So just choose ALU underscore 4-bit, right click on new source, then select implementation constraint file, and here you can write ALU underscore UCF. The long form of UCF is user constraint file. You can see here implementation constraint file. So user constraint file. You can see path. Click on next, then finish. So this is the notepad window. We can see. You can click here on plus sign. So this is our UCF. So select UCF. Click on user constraint. Then click on edit constraint. Now we have to do the pin locking. So first we will zoom it. Right, we have multiple inputs for A, so just see the syntax. We can give net means it is similar to wire, right? Then we have A, that is of 4-bit, so we can write A less than, greater than, then in between you can write bit. So A of 0 that we have. So we are using DigiLearn board. So on DigiLearn board there are multiple switches and LEDs are available. So we are assigning A of 0 to slide switches. So net A of 0, the syntax is lock is equal to this A of 0 is connected to pin number P11. So you can write like this and then put semicolon. Now A is of 4-bit, so we will copy this for 3 more times. I will change this bit. Next bit is 1, 11. Third switch is connected to M4. Right? So there are 3 select line and the last one is output. We will observe outputs on LEDs. So in our program we use variable name is OP. So we can write here OP. So LEDs, there are total 8 LEDs are available on board, LD0 to LD7. So we are connecting OP0 to LD0. So this is our pin number N5. Next output 1 is connected to N4. Third output OP2 is connected to P4. And the last one, this is connected to G1. So there are multiple outputs are there, OP0, OP1, OP2, OP3. Right, so as per board, pin connections are done for A, B, SEL and OP. Now save this file. Then again select your ALU underscore bit file. Click here on plus sign. Then click here, select implement design, right click, run. So after implementation design, we can click here on generate programming file. So this generate programming file will create bit file. And that bit file we have to download on FPGA. Now here we are using basis 2 boards, and that is FPGA. Which FPGA we are using? XC3S250E. So just right click on generate programming file, right click run. So this process is going on. It will generate bit file, and bit file is available in the same folder, that is F drive ALU underscore test. Now the next one is we have DigiLearn software. So click here on triangle. So this is digital software. Here now board is not connected. So we can see here no device connected over here. And settings we can see we have to check there are multiple options: clear status, clear history, then we can see device manager, and here is no device. Now we can just connect our board and we can just observe how it look like. Now the board is connected with our device, right? So the same settings are there. So we are using basis to FPGA board. This is available over here. It has first mode, this is configuration mode. This is FPGA XE3S250E. Same FPGA you have to select in your program. You can see XE3S250E. This is PROM. Now click on browse. Our folder is F drive VLSI ALU. So you can go to the same folder F drive VLSI and ALU underscore test. So this is ALU underscore test and same name ALU underscore 4-bit. So this is ALU underscore 4-bit. Select open. This is warning for us for clock. So click here on clock and then click on program. Same warning is there S. So click on OK. Now here programming is successful. Now we'll see with respect to board how to test our 4-bit ALU. Now this is our laptop through which we have to download code on FPGA. So this is our FPGA board. It is connected towards USB port. This board is from Digilent Basis 2 board. It consists of total 8 slide switches. So slide switches are visible here from SW0 to SW7. 8 LEDs, LD0 to LD7. There are 4 push button switches, button 0 to button 3. Now we have to check that how this ALU work. Now for pin connection, we are connecting A to SW0, 1, 2 and 3. So we are keeping this bit button 1. So this is A0, A1, A2, A3. So A3 is 1. This is B0. So we are keeping B0, B1, B2, B3. So A is 8 and B is 1. So whenever switch is 0, 0, 0, then output should be 8 plus 1, 9. Now whenever the selection line is 0, 0, 1, so we can press this button. This condition is 0, 0, 1. So here you can see 8 minus 1, the output should be 7. Next one is whenever we put this button off, then you can see this is 0, 1, 0. In this case, we have to perform A minus 1. So here we can see A is equal to 8. So 8 minus 1, this will be 7. This is second condition. Now press 2 buttons. This is 0, this is 1, this is 1. Then this is 3. 3 means nothing but what? B minus 1. So B is equal to 1. So whenever these 2 buttons are pressed, 1 minus 1 become 0. The next one is 4. So this is 1, 0, 0. So press 1. It is nothing but AND operation. So A is 8 and B is 1. 8 and with 1, output will be 0. So press this button and check that output is 0. Next one is 1, 0, 1. So this is 1, 0, 1. So press this. So it will perform OR operation. So A is 8 and B is 1. So 8 OR with 1, we can say this will be 9. So you can press the same button again and you can observe the result. So this will be 101. Next one is 110. So 110 is nothing but 6. So in this way we can perform NAND operation.
So A is 8, B is 1. So 8 NAND with 1, you can see output here is all ones. And the last condition is 1 1 1, then we can perform NOT of A. So A is 8, NOT of A we can observe here. So press all three buttons. So this is NOT of A. So this is 1, means your last LED will be off, and this A0, A1, A2 all are 0, means your LED should be on. Right, so in this way we can observe output of 4-bit ALU. Thank you.